In this video, I'm going to go through the process of linear regression, just simple linear regression using the BMI and fitness example. And I will put a link to the original paper in the notes underneath the video description. That's what I'm looking for. The data I have kind of sort of faked to match the paper, so it's not the actual data from the paper. I'm not sure if I was clear about that in the tutorial, but it is often hard to get a hold of the actual data, so this is just going to give us similar results. So if I'm doing a linear regression, I'm always going to start off with a scatter plot. So in Jamovi, we can go to exploration and scatter plot. You may have to have the scatter library enabled. So that's probably that one there. If it's not showing up for you, go to modules and install that. We will put our explanatory variable on the x-axis, and in this case, although this is an association or a correlational study, BMI is often used as a predictor of health, and so this is our explanatory variable, and the paper is looking at whether or not it is a predictor of fitness in this particular group of Chinese medical students. And first of all, we can see it is not a good predictor of fitness. And I do like this paper because I think it illustrates the overuse of BMI as a health indicator. Just as a comment, if you're worried about some part of your health, so if you're worried about your cholesterol or some level in your body, you can actually just go and get that tested. You don't need to use your BMI as an indicator. To my mind, it's a terrible indicator of health, and we should focus on it a lot less than we do. So here they have fitness index, and you can read the whole paper if you want to see all the sort of tests that they ask the students to do in order to test their fitness. And they did have a massive sample, thousands of people participated, and they have standardized the results. So whenever we standardize something, we're centering it at the average. So 0 does not mean zero fitness, it means average fitness, and then a higher number is higher than average fitness, and a lower number means lower than average fitness. And this is quite common to do if you have some kind of measure that's not commonly understood, or you've had to make it up for your paper. I say make it up in a scientific way, like you've developed a new way of measuring something that's suitable for your study. By standardizing it and centering it around 0, it makes it a lot easier for other people to understand what you've done. BMI is just in the regular BMI units, so a few people are underweight, most people are in the normal range, and then there's a few in the high range. We can add a regression line to this, and the standard error too. I don't know if the standard error is helpful because the regression line is trying to predict the average fitness for each level of BMI. It doesn't necessarily predict it well for all people. And we can see here that the relationship is not strong at all. On average, it is telling us that for every increase in BMI, there is a decrease in fitness, but this is not a strong relationship. And to me, it looks like there's a bit of a curve in here too. So once we've had a look at the scatter plot, we would then go ahead and run the regression if it seems sensible. I'm not entirely sure that it does seem sensible in this case, but it gives us a nice look at the residuals and a think about what we could do next. So we're going to go ahead and do it anyway. So in the regression box, we can go to linear regression. Our dependent variable is our outcome variable, and that is our fitness index. And we are looking at BMI. And you'll notice here that there's big boxes here. And this is because simple linear regression is really easy to extend with more variables. And if they're continuous, they're called covariates. And we can also add adjustments in for categorical variables, and they are usually referred to as factors. So in this subject, we're only looking at the very start of linear regression with just the simplest linear model. However, if you go on to do more statistics, you will look at multiple regression and general linear models, and this is basically where it all starts, and we can extend it from here. If we're looking at this, we've got the R, which is the correlation, and the R squared. We don't have the adjusted R squared, which is sort of the correction based on the number of variables in the model and the sample size. In this case, we actually only have one variable in the model, so it's not a complicated model, and we have a massive sample size. So I would say it's not really a problem here, but we can add it in. So let's have a look under model fit, and we can add in the adjusted R squared and the overall f-test. So because we're doing simple linear regression with only one variable, the f-test p-value is going to be the same as our slope p-value, because this f-test is testing, is the model doing anything better than simply predicting the average for everyone? And the average fitness for everyone would just be 0. Well, it would just be the intercept, which I guess because they've centered this technically should be at 0, but I'm not sure if it is, but that might be down to how I have faked the data and not because it's not the real data. So is it doing better than just predicting the average for everyone, whatever the average happens to be for your data set? So if you have more variables in the model, this f-test is testing the whole model. And then these t-tests are testing each parameter separately. But because we've only got one variable, the p-value is the same. Now, the test statistics are not the same because this is an f-test and this is a t-test. So they're different roads going to the same destination, but the test statistic will be different, but the p-values will be the same. So the model is significant. So this means we've got very strong evidence that the model is significantly predicting, I guess, more of the variability than just predicting the average for everyone. But just because something is significant does not mean that it is large or important or useful. So when you have a very large data set, it's easy to pick up significant results. And we do have a significant result here. However, if we look at the adjusted R squared, we're only explaining 9% of the variation in fitness based on BMI. That's a terrible prediction. So if you wanted to predict someone's fitness, looking at their BMI is possibly the worst way to do it. There's got to be much better ways to predict fitness than BMI. So the model is significant in that we do have a significant linear trend. However, it is not explaining very much of the variation. On average, every increase in one BMI is giving us a decrease in 0.08 in fitness in this standardized score. So that's what the slope is telling us. For every increase of one of the X variable, what is the change in the Y variable? Just let that plane go past. Not sure if that's coming through on the mic. So we can have a look at the assumption checks directly in Jamovi. It'll just do them for us. We're not looking at all of these. I guess what we're most interested in is the residual plots. And then we'll look at doing these manually. It probably gives us a little more than we need. So the only problem I have with doing these plots that are automatically generated is it often gives you information that you're not quite ready to think about yet if you're just getting started. The best residual plots I've ever seen come out of Minitab, where it gives you a 4-in-1, and I do like the Minitab version. I wish other packages would do it like that. So what we want to look is to see, are there any patterns left over in the residuals? Are the residuals normally distributed? Is there any trend with the variance? So there is some more stuff that we can do up here, but I'm going to save them and do them one at a time. So I'm going to save the predicted values and the residuals. And then if you go on to study a little bit more statistics, you could have a look at the Cook's distance as well. So back in exploration, the first thing I want to do is just get a histogram of the residuals to look at the normality. Now you can do a normality test. It's relatively common that you can fail the normality test, but I think it's helpful to look at the residuals as well, just to see why it's failing and whether or not it's something that perhaps can be fixed, or we just put up with it. No model is perfect, and it doesn't mean it's not useful in some way. I'm not entirely sure that this model happens to be useful, but but we will still look at it. So for the purposes of this subject, we're just going to have a look at the graphs, and you don't have to run any more tests. So if I go into the descriptives and I put the residuals into the variable, I can ask for a histogram, and they look approximately normal. We do have a little, a few outliers maybe, or some extremer values on the lower end, and there were some people who did score relatively low on the fitness index, but I'm not really worried about it. We do have quite a lot of data. I don't think this is a problem. We do have other problems with the data, but I don't think normality of the residuals is one of them. We are also interested in looking at the pattern of the residuals along the regression line, and that's done by looking at the residuals versus the fitted values. So if we put the predicted values, predicted or fitted, in the x-axis, and then the residuals in the y-axis, we can see what are the errors like across the regression line, and we can add a line in there at 0 if we want to. So it's a bit of a blob. It's possible that there is a little bit of a curve here, and if you want to, you can go and look at the original paper where they fit two different curves to the data to try and get a better fit, and they do improve it a little bit, but it's still just not a strong predictor of fitness. It's possible that we have some increase in variation as well. However, we don't have a lot of observations at the lower end, so this would be probably the underweight end of the BMI scale. There's just not a lot of observations there, so I'm not sure I would read too much into that. So if I was commenting on this model, I would comment on the fact that it's just not a strong relationship, and if we wanted to improve the model, then we could try adding in a curve term. But there is just a lot of random scatter, and it's possible that we would never get a very good model based on just BMI as a predictor, and we would either need to come up with some other way of predicting fitness, or we just give up on using very simplistic health measures as measures of other things which can be measured themselves anyway. So the last thing that you could look at, depending on your data, is the residuals in the order that the data was collected. Now, because this was a big observational study, I'm not sure that that's important in this case, but if you're doing an experiment, it's probably quite important to look at the residuals versus the order of the data. So that means in your data file, you need to create a column of the order the data was collected, and then you can put that into a scatter plot and check it as well. You can probably compute it in Jamovi, but if you've got your data open in Excel, it's probably just as easy to do it in Excel. Okay, I think that's it. If you want to have a go at looking at the normality test, you can. So the normality test is, the null hypothesis is that the data is normal, and this is strong evidence that it's not the data, the residual, sorry. As I say, I don't think that's the biggest problem, and it kind of looks okay. It's not a huge violation here. And you can look at a QQ plot as well if you find that helpful, which is matching up what you would expect from what you got from your data versus what you would expect from a perfect normal distribution, which means that it would line up on a straight line. And it is mostly normal. There's just some non-normality in the tails. But we have a very large data set, so we're failing the test, which is why I tend not to look at this test. I'd prefer just to look at a histogram. But you can look at it if you want to. And you may find that if you have a very small data set for your project, the residuals actually don't look normal at all, and yet you pass this test, and that's because you've got such a small sample size. So I think sometimes this test can be a little bit misleading, and I would encourage you just to look at a histogram so that you can get an idea of the shape of what's going on and the scatter plot of the residuals versus the predicted values.